We'll go ahead and get started then. My name is Mackenzie Skiles. If I haven't met you yet, Chris Dirksen is letting me practice today as incoming chair. So I will be hosting the Center community meeting today. If you haven't joined one, we hold these quarterly through the year. So we'll have another one. Keep an eye out for the next invite. And before I introduce our speaker today, I wanted to mention that we are holding elections for new members for the Center Executive Committee. And we are really looking to diversify the members on our team. So if you are interested in joining the leadership, or you have a recommendation for someone who should join the leadership, we really encourage you to get in touch with us over the next week. You can actually visit the Center website. If you Google Center, you'll find it. It's hosted through the University of Washington. And there is a general email that you can submit your submissions to, or feel free to just send them to Chris or I, or HP, who is the elections chair for Center. And we, like I said before, we're really trying to diversify. So this is not just a US-based effort, it's truly international. So we encourage nominations, self-nominations or other nominations from everywhere and all backgrounds. So we'll be accepting nominations for the next week, and then we'll hold an election after that. And then I will introduce our speaker today. Let me just pull up the introduction here. Today we have Dr. Pablo Mendoza, who is a civil engineer. He got his MS in Water Resources and Environment from the University of Chile and a PhD in Civil Engineering from University of Colorado Boulder. And he's now an assistant professor in the Department of Civil Engineering in University of Chile and a research associate at the Advanced Center for Mining. And over the past 12 years, he's worked on several strategic areas for water resources in countries at different levels of development, including baseline and impact studies related with hydropower generation, assessment of hydrometeorological services, short to long range stream flow forecasting, simulation and prediction of extremes, snow monitoring and modeling, and climate change impacts on hydrologic processes. We're very excited to have him here speaking with us today. There will be time for questions after his talk, and just to keep it organized, if you guys wouldn't mind submitting those questions through the chat box, and I can relay those questions to Pablo. And if you want to take it away.
Okay, thanks a lot, Mackenzie, for the introduction. And I would like to start thanking Jessica and Chris for inviting me. And now I will share the presentation with you. Okay. Can you see it?
Yes, we can see it.
I guess you can. Okay. I only see Keith. Okay. All right. Good afternoon, everybody. Thanks a lot for the invitation. My name is Pablo Mendoza. I'm a hydrologist working at Universidad de Chile. And today I'm going to talk about what we have been doing over the past 3 years. So most of the work that we have been doing in the Andes is reflected in this title, Understanding Snow Depth Pattern in the Exotropical Andes through high resolution remote distance data. So I would like to thank, before starting, to the contributors of this presentation, Thomas Shaw, James McPhee, Keith Musselman, Jesus, Shelley, Simon, Francesca, Alvaro, and Alexis Caro. Okay. To begin this presentation, I wanted to show you a figure that probably most of you are familiar with. This is a figure extracted from the paper by Frödiger et al. which in my opinion reflects very well why do we care about snow distribution in space, right? If we have the same amount of snow water equivalent, its spatial distribution is going to determine how will be the catchment response in terms of runoff generation. So from this figure, you can see that, for instance, if you have a completely homogeneous snowpack in space, you will see a different pattern, temporal pattern in terms of runoff production as opposite with the panel C, where you can see a heavily distributed snowpack. Basically, the snowmelt runoff volume is the same, but the timing can be quite different. So that's why we care about this problem. And of course, understanding snow depth distribution in space and also its interaction with topography, landscape, can help us to configure our snow models. Okay, how can we do more realistic simulations to get runoff production the right timing, okay, which is very important for operational applications, for example. So understanding snow distribution patterns, of course, can help to improve hydrologic predictability. And in the context of where I'm from Chile, and I have the Andes in front of me right now I can look at it. And spring snowmelt runoff accounts for more than 60% of the total atmospheric flow. So all the water that gets stored in the Andes Cordillera snowpack is very, very important for us, okay? So the characterization of spatial variability in snow depth and snow water equivalent has been historically challenged by data limitations. And I've heard lots of colleagues from the US that sometimes complain about data scarcity in the US, but in Chile, it's just dramatic, okay? So past studies describing the spatial variability of snow in the Andes are based on scales larger than 60 meters. So we have very little knowledge about what's happening at the heel slope scale. And of course, we have seen the emergence of remote sensing techniques in snow hydrology studies, in particular, LiDAR technology and Pleiad satellite imagery, which I'm gonna talk at the end of this talk, okay? So snow is important in the Andes, and I wanted to start sharing with you the first official characterization of snow variability along the Andes. This is a report that unfortunately you can only find in Spanish, and the translation is analysis of snow course data across the country, okay? So you can see several snow courses that are located along the Andes. So basically you can get snow everywhere along this latitudinal range, okay? And this report is very important in the snow hydrology history for us, because it provided for the first time a characterization of the seasonal variation of snow water equivalent, spatial patterns of snow density, spatial variations of the snow line elevation, as you can see in this graph. So in the top graph, you can see 3 lines, one line for June, another line for the month of July, and another line for August. So you can see that as you get towards the south, the snow line elevation decreases, and the same type of characterization was conducted for September, October, and November, which are our spring season here in the Southern Hemisphere, okay? And also to provide a little bit more of context, since 2010, we have been trying to set up a research program to better understand the snow in the Andes, okay? And we started very simple. We just started going to the field with the snow probe and measuring snow depth, as you can see in this picture. I think this picture was taken in the Central Andes. Here you can see more pictures of the type of work that we have been doing since 2010. We have been also installing stations to get forcing methodological data sets for our snowmelt models. So that guy that you can see is James. He has been leading this effort since 2010. And since 2014, we have also moved towards the south to an Andean forested environment. Okay, now with the new goal of to answer other questions related with snow, such as the role of interception and how is the interaction between snow and vegetation. Okay. So after many adventures in the field, finally in 2014, the first paper that containing all these manual measurements was published. And you can see it here in this map. All the location of these point measurements of snow depth. These are all located in central Chile, as you can see here. These are 3 pilot basins. And what we found, like from this data set, is that there is a clear altitudinal gradient if we look at snow water equivalent as a function of elevation. And something similar happens if we look at individual catchments. Okay, so 2 key messages that we learned from all this field work, that altitudinal gradients exist, and also that there is a strong dependence with the maximum upwind slope parameter above 3,000 meters, which means that in alpine high altitude in the Andes, wind must be also a relevant driving force for snow redistribution, as found for other alpine sites in the world. Since then, other studies have emerged that have not only made use of observations, but also have tried to combine these observations with numerical models, reanalysis data sets, and also remotely sensed data. Okay, for example, here you can see a swivel reconstruction produced by Edward Cornwell, in which combine a snow energy balance with a fractional snow cover area from modest products in order to create this product along the Andes and understand and get a better understanding of the spatial variability of snow water equivalent, okay, and its relation with stream flow production, which is very important for stream flow forecasting purposes. Then you can see work conducted by the group of Stephen Margulis, and well, this particular one was led by my colleague Gonzalo Cortez, who combined observations, a model, the SSID model, and data simulation in order to get a higher resolution estimate of snow water equivalent. So at this point, he was able to get snow water equivalent maps at the 90-meter horizontal resolution. They replicated the same approach to produce a 180-meter resolution product for 31 years. So this is pretty much the first reanalysis, the first snow water equivalent reanalysis data set for the country. And more recently, Sebastian Murney published this work where he characterized again snow depth pattern, but at the much coarser horizontal resolution, 4-kilometer resolution. So as you may suspect, of course, there has been a lot of progress to understand the spatial variability of snow depth and snow water equivalent along the Andes. But however, the pending question is what's happening below 100 meters, what's happening at the hill slope scale, okay? So this picture reflects a lot where we are now. This is a picture that I took a couple of years ago in Las Valles experimental catchment, which is located in an alpine site above 3,000 meters. So in 2018, we installed many sensors to measure snow depth and other meteorological variables in order to look for answers to new questions that arise from previous studies. So the first one is, how is the spatial distribution of snow depth at the hill slope scale along the subtropical Andes? And also a related question, how does it compare with other regions in the world? Okay, and a more recent question that we have been trying to address is, what is the potential of a relatively new product? What is the potential of Pleiades imagery to characterize snow depth patterns? And eventually, what is its potential for use it to initialize hydrological models. So in 2016, we finally got this guy that I call R2D2. This is a TLS. I'm sure that most of you are familiar with it. So we have been going to the field, to the Vallehermoso experimental catchment and to Las Valles experimental catchment. And so the main goal is to just measure snow, get snow depth maps, as you can see here. So go to the field during summertime, get the snow, get the bird ground elevation topography, and then go back during the winter season to measure the snow depth during the accumulation and then during the melt season in order to understand the spatial distribution of snow, not only here in central, not only here close to Santiago in central Chile, but also along the country. Okay? So this takes us to the main body of results that I want to share with you today. So we have been, over the next slides, I'm going to talk a little bit about the snow depth scaling patterns along the Andes that we have been finding using LiDAR measurements. So again, you can see a picture of our country, very long and thin. And our 3 experimental sites, which are in the headwaters of the Limarí River Basin and the Maipo River Basin, and also the Vallehermoso site, okay? So what we did in this work, which is currently under review in WRR, is to examine snow depth maps in these 3 domains. So the first domain is the Tascadero site, which is located here in the north, Las Vallas site, and also the Vallehermoso site, where we assessed 2 slopes. So one slope where there is some vegetation here. So there are some shrubs scattered that, well, unfortunately, you cannot really see them in the picture because they're quite small, and there are a few trees as well. And another slope also in the Vallehermoso catchment. So here we have a vegetated site and a non-vegetated alpine site, okay? But what is interesting from these sites is that, as you can see, these are sorted from north to south. And if you look at the dryness index, there's a strong hydroclimatic gradient, you know, from very dry conditions to very wet conditions. And that's why, in my opinion, Chile is such an interesting country to study snow, because you can see a diversity of climates, but there's snow everywhere, okay? So in terms of the approach that we used for this particular study, first we aim to characterize the statistical distribution. So how do snow depth statistics vary per elevation band? What is the best probability function that adjusts to snow depth? Okay. Secondly, we conducted a variogram analysis, and this is something that aims to answer the question is there any spatial autocorrelation in the snow depth? Are there any strong scaling patterns? Is there fractal behavior in the snow depth? And then we go to the question of what is a fractal? So in principle, and I love this definition that was provided by Jeff Timms in 2006, a fractal is a structure. It can be understood as a structure that has infinite detail and can be this scaling behavior or self-similar behavior. So many times we talk about fractal scaling, okay? And how can we identify fractals in specific objects? We can use variograms, okay? So variograms is a device that allows to examine whether there is spatial autocorrelation in any specific variable. And even more, we can feed different types of models when we adjust variograms, right? But if we adjust a power law like this, which is equivalent to a linear model in the log-log space, that means that we have identified a fractal within a range of scales, okay? And if we have multiple power laws in the same variogram, That means that we are seeing multi-scale behavior, like you can see in this graph, okay? So this is an idealized case that has been seen in many studies in the past. Previous work by Rebecca Mott, Michael Schirmer in the Swiss Alps, by Jeff Timms in the Colorado Rockies, where they have detected patterns like this in snow depth, like a smaller fractal dimension up to a scale break in the orders of tens of meters, and then beyond, after a scale break, another power law that is holding there, okay? So how can we interpret variograms? The thing is that if you find a multi-scale behavior, if you find a scale break separating these two regions with different scaling regimes, that means that a different combination of processes is governing the spatial distribution of snow depth here in comparison to what is happening here, or in comparison of what might happen if you eventually find a secondary scale break and another fractal pattern beyond, okay? And why do we care about the scale breaks? Because they can eventually be helpful to select model scales, okay? So if you have a fractal pattern, then you can adjust a fractal dimension. And a fractal dimension is just a measure of roughness of a specific surface. So if the fractal dimension is closer to 3, that means that the surface that we're trying to characterize has a more rougher behavior. And whether the fractal dimension is close to 2, that means that the surface that we're analyzing is very smooth. And finally, what we did is to answer the following question, okay? If we detect scale breaks in snow depth, like we're seeing here, is there any relationship between these scale breaks and the distance between the local maxima snow depth values that we can find along transects? And this is following the spirit of previous work by Kevin Shook and Ernesto Trujillo, which suggested that it is possible that there are links between these scale breaks and snowdrift formation. Okay, so question number 1, but these are a lot of questions, so please have patience. What is the relationship between snow depth and topographic variables? So here, what we're seeing are snow depth maps for our 4 experimental sites. So from north to south, recall that we have Tascadero, Las Vallas, Valle Hermoso West, which is the only site that has some vegetation, and Valle Hermoso East. So recall that here we are in a dry region, and towards the south, we're moving to a wetter region. And here we can see the dependency between snow depth and elevation, slope, and northness, together with Pearson correlation coefficients and Sperman-Rank correlation coefficients. And the red lines are simply connecting the mean values within each interval or beam, okay? So as you can see here, for instance, in Tascadero, we did not find a especially strong relationship with elevation for this particular subdomain, but what we did find is that snow depth increases up to some elevation and then decreases again, a behavior that has been reported in other subdomains, in other mountain regions of the world. And also we found like a very strong dependency with northness, okay? And a similar pattern, well, except that perhaps the only site where we actually found a strong elevation gradient was in BH West. So in summary, strong relationship between snow depth and altitude in Las Vallas, this site, and BH West, decreasing snow depth with higher elevation in alpine non-vegetated sites, and also strong dependence with northness in all these sites. The next question, how is snow depth variability across elevation bands? So what we're seeing here is the band average snow depth as a function of the mean elevation within each elevation band. So these are 25-meter elevation bands. The different colors are showing the results for different sites, okay, together with the sperm and rank correlation coefficients, which reflect the strength of the relationship. So as you can see here, the altitudinal, any possible altitudinal dependencies are quite site dependent, and the same is observed for when we assess standard deviation, coefficient of variation, and skewness as a function of elevation, okay? So in summary, there are different trends in mean standard deviation and the coefficient of variation. The other thing is that snow depth is positively skewing most elevation bands across non-vegetated sites. How can we best represent the distribution of snow depth? Typically, in many land surface modeling scheme, there are fixed subgrid parameterizations that past studies have assumed. Like for instance, the snow depth can be represented by a log normal distribution. Okay, so we wanted to test whether the log normal distribution is the best, or if it fails, which one is the most appropriate. Okay, so what you can see here for each site are histograms of positive snow depths together with the fit of probability functions. So you can see the results for the normal distribution in gray, log normal distribution in blue, and gamma distribution in red. And together with goodness of fit statistics, so smaller values indicate that the function provides a better fit for this variable. And we repeated the exercise for different elevation bands. So for instance, here we can see Anderson-Darling statistic values. The smaller this value, the smaller value you get, that means that you're having a better fit, okay? So we conducted this analysis for the full domain, as you can see in this panel, and for each elevation bands. So what we found is that the log normal distribution is outperformed by either normal or gamma distributions, and that gamma distributions perform better than log normal distributions for full domain. And what is the implication of this? That first, that we should be more careful when we select subgrid parameterizations, and more than a couple of studies should be revisited based on this result. And then a question that has fascinated me for many, many years, since I took a multi-scale hydrology in 2011, and I was introduced to the fractal concept. Is there fractal behavior in snow depth and topography in the Andes? Because such behavior has been reported in many studies, as I said before, in the Swiss Alps, in Austria, in the Colorado Rockies. Can we find the same behavior in the Andes? And here you can see omnidirectional variograms for our 4 sites. The vertical lines are showing scale break lengths. The different colors represent the results for the different sites. And the diagonal black lines are showing that we have a power law with a fairly good fit, okay? Which means that there is fractal behavior. So the answer is yes, there is a fractal behavior. Indeed, there is multi-scale behavior. We found up to 3 different scaling ranges, which is quite intriguing. At least the third one was completely unexpected to us. And then we repeated the exercise with topography to see if there is any link between the scale breaks that we were detecting for snow depth and for topography, and the answer is not. So in summary, scale breaks span 15 to 21 meters in vegetated areas. This is, again, very, very similar to what has been found in other alpine sites elsewhere. There are shorter scale breaks in BH West, which is a shrub-dominated site. And there's not a clear connection. Although we see a fractal pattern in topography, there's not a clear connection between the scale breaks in bare topography and those that we found for snow depth. And finally, we took a look to the snow depth transects. So here we can see again the Vallehermoso site, which is the most southern study area. Here you can see the transects that we could get for this couple of sites. So these transects have an orientation northwest, southeast. These are for the vegetated site, BH West, and the unvegetated site, BH East. You can see higher frequency variations in BH West, which is expected given the presence of small shrubs and a few trees over this domain. And then what we did is to take a look at the distance t, okay? Basically following the same spirit as Ernesto did in 2007. Take the distance t between the local maxima peaks and then plot the density, the empirical density, as you can see here. And the results are showing that the average, so here you're showing the distribution of such of this d distance, but for different directions, for different transects, west-east, south-north, northwest-southeast, southwest-northeast. And what we see is that for this vegetated site, these values are smaller and similar to the fractal dimensions that we found in snow depth barograms for this particular site, okay? Which are at the same time smaller to the values that we found in VH East, which, remember, both sites are neighboring sites, same hydroclimate, but different landscape conditions, okay? And what was more surprising for us is that the results are very similar to what we found in Tascadero and Las Vallas, which are our northern sites, okay? So this result is very important. So first, that the primary scale breaks are of the same order of magnitude as the mean G values, but also the similarity of results that we found between VH East, Tascadero, and Las Vallas. That suggests that landscape properties are more important controls on the snow depth variability rather than hydroclimatic conditions. Okay, I have talked a lot about R2D2, and this guy that you can see here, Dr. Thomas Shaw, he has recently moved to WSL. He contributed a lot in all the field campaigns that we have and in all the processing of LiDAR data sets. So I'm going to talk a little bit more about what he led before he left and where we are in terms of the use of remote sensing techniques to better understand snow depth patterns. So the next question is that, okay, we have this LiDAR and we're learning a lot from it. So how can we use it to validate new technologies, okay? And the new, relatively new technologies are Pleiades. Pleiades imagery, okay? So what Tom did during his postdoctoral work was to study this catchment, this glaciated catchment of the Yeso River Basin. So you can see that there are 3 glaciers, approximately 12% of the total area. And he aimed to answer 2 questions. To what extent can the information derived from Pleiades emulate what we're seeing with LiDAR data? And the second is, what is the added value of using Pleiades information to initialize hydrological models? Okay. So for those who are not familiar with Pleiades, so each image is basically comes from a triplet. So what Tom did is to analyze 2 triplets, okay, in order to get snow depth maps. So one triplet with snow. So if you're very careful, you will count 3 and you will see that each image is repeating, and that's how you complete a triplet, okay? This is the snow on triplet that was acquired in September 2017. And this is the snow off triplet that was acquired in the summer of 2018, okay? And the principle is quite simple, okay? The snow depth can be computed as just the difference between those maps, okay? The snow on map and the snow off map. So here I'm going to show some validation results that Tom got from this work. So this is the whole catchment, but LiDAR measurements were available only in this subdomain together with snowproof measurements. So here you can see the LiDAR-derived snow depth map to the left, and to the right, the Pleiad-derived snow depth map. So the Pleiad products are at the 4-meter horizontal resolution, okay? So for comparison purposes, the LiDAR-derived original map, which was at the 0.5-meter resolution, was rescaled to 4-meter resolution, okay? Oops. So here in these maps, you can also see transects, okay? And what I'm showing here is that is a comparison between LiDAR snow depth and Pleiad-derived snow depth along the red transect, okay? So in general, we can see that Pleiads can get the spatial variability of snow depth that Pleiad provides, but it is much noisier. And some corrections are necessary, especially on steep slopes, and also in those areas where we have shallow snow covers. Okay, but overall, what Tom found in his analysis is that there's a great potential in the use of Pleiad to reproduce snow depth, and also when assessing the added value to initialize models, he found that initial hydrologic conditions that you can derive from Pleiad, the snow depth derived from Pleiad, combined with the model for snow density, and putting that together to initialize a hydrological model can give you improvements in terms of fractional snow covered area, snow mode, glacier mass balance, and stream flow estimates, compared to our alternative estimates of initial conditions for sweep. Okay, just to close the presentation, what we have found so far using high resolution remotely sensed data, in particular TLS technologies, that there is multi-scale behavior in snow depth in the extratropical Andes. The primary scale breaks that we're getting are of the same order of magnitude as other mountain regions in the world, as you can see here. Our results suggest that scaling patterns of snow depth are more dependent on local landscape conditions rather than hydroclimatic characteristics. The similarity between the scale length D of the snow drifts and the scale break lengths detected from barogram analysis that suggests that there is strong connection between the two of them. And finally, we're finding that there is great potential on the use of Pleiad imagery, and not only to characterize snow depth patterns, but also to improve hydrologic simulations during spring and summertime. Okay. And finally, of course, there are lots of new opportunities for international collaborations in order to improve measurements and also modeling capabilities. And this is the end of my talk. Thank you very much for your attention. And I'm happy to take questions, comments, and suggestions, of course.
Thank you, Pablo. It was a great talk. If there are any questions, if you wouldn't mind putting them in the chat box. And we do have a question first from Jessica. This is a fun question. Do you really have 6-meter deep snow in your Eastern study plot, and how do you survive digging snow pits?
6 meter, I've never seen, well, who knows, because there are large uncertainties in LiDAR-derived snow depths. I don't know where she saw that value. I don't know if she saw it.
Maybe it was a drift in one of your
from the LiDAR map, or maybe
maps.
from a drift.
It was the drifts kept going up to 6 meters in one of your plots.
Okay.
You're finding it now.
Yeah. Well,
yeah.
I've heard of 5 meter. I've heard of 5 meter, but maybe
this one.
Yeah.
Right here.
Well,
VHs kept going up to 6 meters.
It is possible, but also at the same time, there are large uncertainties on steep slopes on our later data sets.
We have another question from Peter Kirchner, and that's, do you expect differences due to the latitude between basins due to differences in seasonal sun geometry?
On seasonal what?
Sun geometry, so just sun angle.
Sorry, I don't understand.
Basically, so between your basins across your latitudinal gradient from top to bottom of the mountains, you'll get a different sun angle across those basins. Yeah.
It is possible. Yeah. So orientation might play a key role in the snow distribution. So it is possible. So that's definitely something that we would like to take a look at. I take a look at other slopes in the same catchment and also take a look at other LiDAR measurements for different types of years.
Yeah,
and
so,
actually,
sorry, go ahead, Pablo. Hi, how are you doing?
Hi.
Yeah, just to expand on that, because Chile has such extreme variability in latitude, it may offer a unique opportunity to investigate that. Because, for example, in the spring, depending on the latitude, you can still have snowmelt processes happening near the solstice, whereas in some locations it may happen much earlier. So there's a multivariate process going on there that's impacted by aspect intensity or northness, as well as the timing of the discharge and the snowmelt.
Okay, thanks a lot, Peter, for the comment. This is quite valuable for us because I feel like all these results are leaving more, I mean, we're getting a lot of new information, but at the same time, they're opening lots of questions to go to the real questions, which are related to the why. Why are we seeing what we're seeing? So there are many things that we have found, like for instance, this third scaling regime that we still don't know why are we finding it. And I think we should definitely keep working on that, especially in terms of complementing with new types of information. For instance, from wind models, wind flow models, to see if there is any relationship with that. But thanks for the comment.
Yeah, we're grappling with the same questions in Alaska, so I don't think anybody has it figured out yet.
Okay, cool.
Okay, 2 more questions for you, and we'll maybe move through these kind of quickly and people can follow up with you afterwards so that we have time to get to Timbo's talk. But the next one is from John Pomeroy. Have you confirmed multifractal behavior to snow depths? We found simple fractal scaling for uniform fields and specific mountain slopes, but scale breaks beyond those landscape units that suggest multifractals.
No.
That question is in the chat too, if you want to reread it.
Yes, thank you. I'm actually reading. My English is terrible right now because I've been only speaking Spanish for the last months, but that's why I'm looking at the chat. Thanks, John, for the question. Actually, what I was showing is multi-scale behavior, which is different to multifractal. Multifractal is supposed to involve a continuum of a spectrum of fractal. Maybe you reviewed this paper because I got a comment like this from one of our reviewers. If we were actually finding multifractal behavior, and the answer is not. We also found like up to 3 scaling regimes, which can be described as multi-scale behavior.
Okay. It's good not to find multifractals because it would really mess things up. And we would introduce a tremendous scaling problem into snow models. But there are hints at multifractals as we get to larger scales. Continue to be interesting.
Cool. Thanks, John.
Great. And then a final question from HP. Do you think the noise in the stereo Pleiades depths is coming primarily from the snow off or snow on DEM?
Oof. That's hard. I don't feel qualified to answer that question. I don't know if James wants to complement because I see him connected, or he doesn't want to talk.
We need Tom here. I don't know. I don't really have a feeling for that point, which is it's an important point, definitely.
Yeah.
If there's vegetation in the basin, it's probably the snow off. But
yeah,
that's
no,
just
but
my.
in that particular basin, there is no.
Yeah, this is as dry as it can get.
Yeah.
Yeah. So what we did find is that the largest differences with lidar derived snow depths are on steep slopes, and also when you have shallow snow covers. So that's why we should be. There is a lot of potential to apply Pleiades, but of course there are some corrections to make. But for us, that information is super important, because in the Andes we have nothing. It's really depressing.
Thank you. Great talk.
Thank you.
Thanks, everybody. Next, we'll move to early career talks. So these ones are a little bit shorter. They're 15 minutes to introduce a topic that an early career researcher is working on or has worked on for their PhD. And our speaker today is Dr. Timbo Stillinger, who's a postdoctoral scholar at the Earth Research Institute at the University of California, Santa Barbara, where he works on improving real-time forecasts and climatological understanding of water supplies stored as ice and seasonal snow. His research is on both the physical science of measuring water from space and the linkages between hydrology and how humans manage their demand for water. Timbo earned a bachelor's degree in molecular environmental biology from UC Berkeley, a master's degree in environmental science and management from UC Santa Barbara, and a PhD from UC Santa Barbara. His PhD focused on the longstanding and difficult classification problem of snow and cloud discrimination in multispectral satellite data, and the impact of runoff forecast uncertainty on water management and headwater basins. And today, I believe he's going to be talking to us about cloud discrimination. Timbo, if you want to share your screen, you should be a co-host.
Yeah, I'll do that right now. Can you guys hear me?
Yes.
Cool. Thanks for that introduction. And start. Can you guys see the slideshow?
Yes.
All right. So yeah, thanks so much. And thanks for your talk, Pablo. That was really interesting. Today, I'm going to talk to you guys about a slightly different aspect of snow hydrology, looking at kind of spatial methods for discriminating and telling the difference between snow and cloud. So to get started, since we're all the snow hydrologists here, I won't really belabor the point, but properties of snow are really useful for a wide variety of applications. Kind of knowing the area of the earth that's covered in snow and the surface properties of that snow is really useful information. And one of the best ways we have to get those measurements is from satellites in space. And this is compared to kind of the pictures on the bottom here, which is where you could actually go out into the field and take the measurements, which in some areas of the world, it's actually not trivial to get to the snow. Once you find the snow, just finding a safe spot to take measurements is kind of difficult. And then it can take a long time to acquire those measurements. So satellites offer a unique opportunity to kind of get global estimates of the surface properties of the snowpack. But one of the big problems when we're measuring from space is that you tend to have clouds that block the view of the optical sensors. So this top picture here is a picture from MODIS with a red box over an area where we have zoomed in views from Landsat. And on the bottom left, this is what you'd hope to see every day, which is a nice clear view of the snow in the mountains. But the two pictures on the right are more what you actually end up seeing most of the time, which is some partial cloud cover or complete cloud cover. And being able to tell the difference between the pixels and if they're a snow pixel or if the pixel is obscured by clouds is really important when you're trying to estimate the physical properties of that pixel. And one of the difficulties is that you can actually have pixels that are snow covered or obscured by clouds that have very similar spectral properties in these broad bandpass multispectral satellites. And so this is a figure out of a paper that I published as part of my dissertation with Jar Roberts and Natalie Collar and Jeff Dozier. And what we were doing is we took a spectral library of a whole bunch of snow pixels and a whole bunch of cloud pixels from Landsat 8. And then we use those as the optimization goal for a radiative transfer model, where we took snow pixels and we said, okay, try and give us optical properties of a cloud that match these reflectances and these band passes. So trying to model snow as clouds and then trying to model clouds as snow. And one of the outcomes of this was that in these broad multispectral band passes, you actually can derive solutions that are realistic for the same pixel, modeling it as snow or modeling it as cloud. And these tend to be for thinner clouds and for lower fractional snow-covered area pixels, where you have something else in the pixel that has brighter reflectance in the sphere bands that makes it harder to discriminate. So two key findings from this were we need some other methods besides the spectral signature to tell the difference. And also, if you look at the graphs on the bottom, if there was an image, if you had an imaging spectrometer, you wouldn't have these discrimination problems. So even for the most spectrally similar pixels in multispectral satellites, imaging spectrometers would have no issue telling them apart. So what we need to do is start to think past the pixel and look at some of the other characteristics of these objects. And when you start thinking about the size of what you're interested in measuring in relation to the size of the pixel, as the objects get larger relative to the pixel size, there's lots of other attributes that you can use to give characteristics to those objects to help you determine what they are. And so what we see over in box A is maybe what we're more used to thinking about with snow, because we talk about fractional snow-covered area a lot. But when we look at an image from space, you can actually see that if we think of the snow as actually a mountain snowpack and clouds as objects, these objects actually span distances far greater than a few pixels. And so maybe there are some unique characteristics at the landscape scale that we can use to discriminate clouds from snow. And so what I'm going to do now is I'm going to go through kind of from really simple to really complex features we can use to tell the difference between them. And kind of at the most basic level, clouds and snow just have different distributions and kind of the variability in the spectral signature of pixels that are next to each other. So if we think of just looking at one visible band from a satellite, and we look at 4 pixels that are next to each other above a mountain snowpack, you're probably going to have a lot of variability in the measured reflectance in that band among the 4 snow pixels. And that's this conceptual model down here on the bottom. And then in the cloud, you can see the cloud pixel, the idea is that, okay, well, 4 pixels adjacent to each other are more likely to have more similar spectral reflectances, because clouds in general have a more homogeneous texture to them, as you can see in this picture of the Earth up here, where the clouds are clearly visible. And this graph over here shows that, where if you just look, the probability of finding adjacent snow pixels with variability in reflectance in the same band is much greater than for clouds. But you can't really use this alone to tell the difference between them, because there still are instances where you find cloud pixels where next to each other they tend to have some variability in their reflectance. So kind of the next step up in getting complicated is you can pick a more complicated filter, in this case a Gabor filter, where you can tune it based on variable parameters that are in it to maximize the difference in response between snow and cloud pixels. So this is an example of a convolutional filter, which is this GIF here is showing. If you think of the blue image as a band of your multispectral satellite, the gray image that's 9 pixels wide that's going across the image is the convolutional filter. And you're basically applying this filter in little windows across the image over and over. And the output, which is this green image up here, is the response from that filter. And the idea is by tuning the filter with these various parameters, you can maximize the response for snow areas and minimize the response for clouded areas. And that's what this graph over here on the left shows, is that you can tune a Gabor filter so that above a certain threshold, no cloud pixels basically pass the filter, but most of the snow pixels do. But now you're still left with the problem that on the left of this red line, there still are some snow pixels that don't pass this convolutional filter. And this is pretty common with any sort of image processing filter. When you do convolutions, you only tend to elicit responses in some of the pixels of the object you're measuring. So you need some way to categorize pixels that are close to each other as part of the same object. And so one way you can do that is that you can use superpixels to over-segment your image and give some characteristic other than a pixel to determine what things are in the image. So these were originally developed for regular red, green, blue imagery, where they would take basically the Euclidean distance between the brightnesses in the color space, along with the spatial distance between the pixels, and assign in local clusters each pixel in the image to a bigger superpixel. And what we've done is we've taken that same approach, but applying it to a multispectral satellite where you have many more bands of information. Instead of using a Euclidean distance to tell how spectrally similar pixels are, we use a spectral angle mapper. And then we still use the spatial proximity to basically over-segment the image. And this is an example in the Landsat image into areas of local similarity. And once you've done this, what you start thinking about is, okay, well now if I just assume that each superpixel only consists of one type of surface, I now can use the attributes and characteristics of that superpixel to classify the superpixel and apply that classification answer to all the pixels within it. So one example of doing that with the Gabor filters is here. And I'll just mention the top part of this figure today. But if we take the 15-meter panchromatic band in Landsat, which ironically is the band where spectrally clouds and snow are the most similar, so you wouldn't be able to set a threshold necessarily and tell them apart. If you apply this Gabor convolutional filter instead of threshold, you can see all the pixels that you've elicited a response from. You can then look at the superpixels you've created for the image, and then if a superpixel has greater than, say, 10% of the pixels within it that pass that filter bank, you can then say, okay, we're confident those are not cloud pixels. We're confident that we're seeing the snowpack underneath, and we can confidently keep those from being included in the cloud mask. This is another example of using that same approach with a coarser multispectral satellite, and this is off GOES 16, so the Eastern US GOES satellite, where we take the red band, and then here's a false color image of it in panel B, and we look at the operational cloud mask. And this highlights kind of the main problem with the operational mask, is you can see the black pixels are what the satellite operational mask thinks are cloud cover, and it's accidentally masking quite a bit of the snowpack. So we can segment the image into superpixels using the spectral angle and the distance between the pixels. When we pass the Gabor filter bank across the image, we can then find those superpixels, which are highlighted here in blue, where we know the response is high enough and enough of the component pixels that we're confident it's not cloud cover. And we can then remove those pixels from the cloud mask, resulting in a better cloud mask that leaves a lot more snow pixels you're confident in to get measurements of. So now the next thing I'm going to talk about is kind of the latest thing I've been working on, which is the next step up in complication for including these kind of image filter banks for processing the images. And these are called convolutional neural networks. And this is basically a really nice framework for automating, optimizing the selection of your image filter banks at massive scale to get the answers you want to segment the image. And so if you look down here, you can see at the bottom left of the screen are the two figures from earlier slides where I showed you very simple examples of a single filter type you could use to potentially tell the difference between clouds and snow. And instead of using these, what a convolutional neural network does is it stacks thousands and thousands of filters on top of each other where you don't know what the parameterization of them is. When you start, that will elicit the highest response from snow and not a response from clouds. And the way you tune them instead of manually fiddling with the parameterization is you feed it an image that's already been segmented and you let it iterate millions and millions and millions of times until it optimizes the tunings of all the filters to minimize the error when it classifies the image into different classes. And this is a really common method for segmenting the pixels in imagery for computer vision techniques outside of snow hydrology. And the real crux to this is in order to optimize the network, you need labeled training data that you can use that the network can learn from to optimize the weighting of all the filters. And well, the sensor I'm most interested in now are these coarser multispectral sensors like GOES and MODIS and VIIRS. And the real problem with these is that it's really hard for a human to manually go in and mask out every pixel in the image of snow, cloud, or neither of those. And the other problem is to get these convolutional neural networks to work really well, the rule of thumb is you need between 5 and 10 million labeled images that you train it on to reach human level performance. And manually going into these and labeling that many would just take a really long time. So instead what I do, which is I automatically create the training data at scale based on the output from other algorithms. So this example here shows on the left the image of from this day that MODIS captured, where you can see there's snow and clouds. Some of the snow's over the clouds. It's kind of hard to tell them apart. And so what I do instead is use a new spectral and mixing algorithm that I've been working on with Ned Baer and Jeff Dozier, where we take one clear sky image from the summer with no snow. We take our estimate of the fractional snow-covered area and the other snow properties of that snowpack from that algorithm, which has the advantage of we look at every day of the year. So even on days when there's cloud cover, we don't have a clear idea of what the snow property was that day, we smooth through time the answers and we can get a better idea. And we can then use that output to get basically what is the modeled reflectance in the bandpass of the satellite for that snow that we unmixed on that day. And we can blend it back in with the background image and create a synthetic image without clouds, with a snowpack, with modeled reflectances of what we would expect to see in those pixels on those days. And alongside that, we also get a labeled image based on the snow cover map. So with this method, we can basically create an unlimited supply of labeled training data. And this is an example. So what we do here is to get labeled examples of snow. I take the full image stack of the 20 years of the MODIS record, and I create daily masks of snow and snow-free areas and label them to use for training the neural net. And then to get labeled images of cloud cover, I just go to an area where I know there's no snow and it's really easy to identify the clouds, which is over the dark ocean. And there is also a large collection, basically unlimited supply of labeled imagery. If you go to ocean MODIS pixels, you use the mod 35 cloud mask over the ocean and you use that to label all the clouds. And you can see that here on the left. These are examples of cloud cover that I've labeled as cloud or clear. And then on the right are examples of snow cover labeled as snow or clear. And then when we train the neural network, we can then look at the output afterwards and see, well, does this work? And so the first step is, okay, if I feed it a real image from MODIS on a day I knew was cloud-free, even though I only trained it on fake images of the snowpack, can it actually identify the snow? And it looks like it actually can. So this is the image that we fed into the trained network on the left. This is the output of the snow mask from it. This is then the output of the cloud mask, which you can see has some misclassifications in it, mainly the dark water bodies in the mountains, which is probably because we trained it on clouds over the ocean. You can see the labels that come out of it. And then the really important part is when we compare our cloud mask and our snow mask to the operational cloud mask, we can see that in the final panel over here on the right, basically all the pixels that the operational mask accidentally identified as clouds, but is actually snow, that our neural network correctly identified as snow cover. And so if I go back here, you'll notice some interesting things about this training network is you never have clouds and snow in the same picture. You never have clouds over the land surface. And you never have an actual image with real snow in it. All these are modeled pixels of snow cover. So the next thing to look at is, okay, well, what happens when I feed it an image where we have clouds over the snowpack? And it's basically a type of image that the network's never seen before. And it turns out this works quite well, and it's pretty awesome. So the picture here on the left is a much more difficult Modo 9GA acquisition. You can see the cloud cover over the Sierra Nevada. You can see the neural network picking up the snow and the snow mask. You can see it also correctly identifying the cloud and the cloud mask. Then we have the labeled image here that shows you those differences. And then the panel over here on the far right is basically all those pixels that the operational cloud mask said was snow, but we know said was cloud, but we know is snow covered, and that our neural network was able to correctly identify as snow cover. And then down here on the bottom is some training metrics, just looking at how well the neural network performed on the full library of training data at the very end of the training. And the important thing to look at here is that basically it can learn to never mix up clouds and snow on the training data, which is really cool. And the global accuracy of this was about 81%. And this is still pretty preliminary. I can talk more later about some of the next steps for this, but This was trained on a neural network that I designed from scratch, and I only trained it on about 14,000 images. So the goal now is to scale it up. I'd like to get closer to that 5 to 10 million image mark. I'm only training it over the Sierra Nevada right now. I'd like to include other areas, and I have some ideas for synthetically mixing clouds over the snowpack and getting labeled images to use for training. And so the nice thing about this is it takes a long time to train these, but once the algorithm's trained, actually processing an image takes less than a second on a single CPU. So while training is difficult, operationally integrating some sort of cloud mask like this into other products is not resource intensive, and it's very fast. And that is my talk. So thanks very much, and happy to answer any questions.
Thanks, Timbo. I think the putting questions in the chat worked well for the last one. If we can continue doing that. And Timbo, you can see them as well, but this is a question from Peter Kirchner. Can you train the neural network on the full range of snow reflectance properties, e.g. dirty snow, different grain sizes, wet snow surfaces?
Yeah, that's a good question. So I didn't really talk about it in too much detail, but the model, our model for modeling the snowpack in our spectral and mixing algorithm, the way that the model is parameterized is that it uses the fractional cover of the snowpack, the grain size of the snowpack, the solar zenith angle of the illumination of it, and then the contaminant concentration in the snowpack. And I'm pretty sure we can also, so for the cloud model, we can change the phase of the liquid, if it's ice or liquid in the model too. So we are able to basically give it a whole bunch of different snow properties. And then the other cool thing, so this kind of goes into HP's question next on including other spectral bands. So another unique part of our snow mapping algorithm is the way it's been written and coded is that you can feed it any band passes you want within the electromagnetic spectrum to give it what you would expect the surface reflectance measurement to be in those band passes. So while I trained it on MODIS data, it is very simple to take our snow model and basically feed it other basically make it produce a map in very different wavelengths. So you would be able to add different spectral bands like HP was asking in the next question. And kind of big picture, the next thing I'm personally looking to do is once it gets working better on MODIS is to try and deploy it on GOES. So.
Great.
And then,
oh, sorry, keep going.
Yeah, I see the next question from Elias about the operational mask being pretty aggressive. So the next step to what I'm working on, it's really tricky finding labeled imagery in MODIS of snow and clouds in the same place. So I have a library of Landsat images that have been manually masked, and then my plan next is to take the neural network approach and run it on the MODIS scene that was acquired within about 15 minutes of that Landsat scene and look at the global accuracy for the approach on those. And that's similar to what I've done with the operational MODIS mask, which is very aggressive. It tends to be conservative and assume things are cloud when it's probably snow.
Great. Any other questions? Okay, if you do have questions, oh, yes, there are more questions. Okay, they all kind of popped up, but from Jeff Dozier, the topography has a pattern based on solar illumination and gradients of the pixels. Can you use that information?
Yeah, so that's a good question from Jeff. And you can. So if you know the topography and the location of the sun, depending on the spatial footprint of the pixel, when the satellite took the picture, you know what the local illumination would be, especially the pixels that are sunlit or shaded. So as you can see in the Landsat picture back here, there's a whole bunch of Landsat pixels that are just in full shade. And so you know that expected pattern of shade and sunlit pixels. And when a cloud goes over that, it obscures that pattern. So even here in this Landsat picture, you can see bright pixel or spectral reflectance values from a cloud pixel that maybe are physically realistic for being snow could definitely be in a place in the image where you're very confident there's no way you could have a pixel that bright. And then there's some other approaches too with like histograms of oriented gradients where there's an expected orientation to the brightness histogram in each place of the image, given the topography and the shading you could use. And then the next question was about the height of the clouds. And right now we don't use anything with cloud height. It's just the texture of the clouds. And training the network is just basically what does the cloud look like spatially. And then Sam Tuttle asked about training the images over land areas with no snow. And yeah, that's a really good idea. I think that would work really great, especially because there's areas very far away from snowpacks that have land cover types that are very similar to those at the base of the mountains. And so if you found regions where you were confident there was no snow, you could probably train the network with those images and then apply that on the snowy areas. So yeah, I think that's all the questions.
That's all the questions. And if there's more, you can always follow up with Timbo after this talk by sending him an email. And I just want to thank everybody for joining this quarter annually center meeting. Like I mentioned at the beginning, we will have another one coming up, and we are always taking recommendations for speakers as well. So if there's somebody that you would like to hear from, we would like to hear from you. And if I don't see you all before then, we'll see you on the next center call. Thank you for joining.
Bye. Thanks.